Hi, welcome back to my channel. After knowing the notations and symbols to be used under ultimate strength design, this video now is about assumptions and provisions in analyzing and designing your reinforced concrete sections. Ultimate strength design of beams. In here, we will be discussing provisions and assumptions of ultimate strength design taken from 2001 and the latest edition of NSCP, which is 2015. So knowing the provisions and assumptions that we can apply in analyzing and designing our reinforced concrete under USD is important because it would be easier for us to accept the steps and accept the techniques that we have derived and to be utilized in the analysis and design. So here, we start with your basic design relationship. It's very simple that your resistance should always be at least equal or greater than your load effects. Here, your load effects would be your demand. Your load effects is caused by your loads or load combinations, in particular for UST. What does it mean? If you have dead load, if you have live load or earthquake loads, those loads would induce effects. And those effects would be termed as the demand of our, let's say, situation that needs to be resisted or needs of resistance. The resistance can also be termed as your capacity. Ibig sabihin, pwede nating i-term na the basic relationship is that capacity should at least be equal or it should be always greater than with your load effects. So where do we get our capacity? Your capacity is, of course, taken from your section. So if your section is singly reinforced, assuming there is tension bars at the bottom, and then base is here, the overall height is H, and then this is AS, so your capacity could be taken from this section. We've already initialized the capacity of your section under working stress design, but this time we'll be particular with ultimate strength design. Continuing, for your resistance, what we have is your nominal resistance, R sub n. So your nominal resistance is with a symbol or presented here as R sub n. And by definition, let me just clear my screen. By definition, it implies that the resistance is a computed value based on the specified concrete and steel strengths and the dimensions shown on the drawing. So the drawing means that when illustrated, as mentioned before, your resistance comes from your section, the base by H relationship, or the depth of your tension bars o kaya sa area ng tension bars mo. Kasi nga resistance siya, that's the capacity of your given section, kailangan taken siya dun sa characteristics and properties ng materials used of your sections. Consequently, you have your required strength. Ano naman yung required strength natin? This is taken from the combination of your factored forces. Here, we have your load combinations taken from the NSCP 2001 and NSCP 2015. What we have seen on the left are load combinations. Combination of dead load, live load, followed by dead load, live load, and wind load, followed by dead load and wind load, followed by dead load, live load, and earthquake, and then dead load and earthquake. There are other load combinations, but we will just focus on these combinations that matters for this quarter. But again, there are other load combinations taken from the NSCP. Okay, you can just check that on your free time and double see, or see what are the other load combinations. But in particular for this 5, these are your load combinations. Under 2001 and 2015, we will differ this two. Okay, we'll start with 2001. 2001, if your situation gives you dead load and live load, the load combination should be 1.4D plus 1.7L. Meaning, you multiply your dead load by a factor of 1.4 and your live load by a factor of 1.7. Continuing the NSCP 2001 provisions, if using dead load, live load, and wind load on the analysis or design, you need to use this load combination, 0.75 multiplied by the quantity 1.4D plus 1.7L plus 1.7W. Again, D is for dead load, L is for live load, and W is for wind load. Followed are other load combinations under dead load and wind load combination, dead load, live load, earthquake combination, and dead load and earthquake combination. Here, in this section, it is specified how it is your U, yung U natin, yung ating load, no? Ultimate load. Sometimes it could be presented as WU. Okay, if it's just a uniformly distributed load, let's say from a simple span. No, kunyari, nakaganyan tayo. Okay. WU. Tapos this is a simply supported, just assuming length L. And then this is my, if we say that my dead load is equal to 10, my live load is equal to 15, therefore, we can compute for WU under 2001. Now, pag 2001, it's equal to 2001. It's equal to 1.4 times 10 plus 1.7 times 15, which would be equal to so according to my computation, it is 39.5. Again, W is computed using the dead load, live load, load combination for NSCP 2001. What if it becomes 2015? Let's just change this one. Paano naman ina-apply yung 2015? Dead load is still 10 and then live load is still 15. So, babaguhin lang natin, gagawin lang natin na 1.2 times 10. So, 1.2. Sorry for the pangit na sulat, no? 1.2 times 10 plus 1.6 times 15. That would yield to a value of, let me check, 36. Okay, 36. Ibig sabihin, kapag ang provisions na ginagamit is 2015 under dead load and live load combination, your W becomes 3.5 less compared to your WU in 2001. Pero it should be specified in the problem what combination to use. In cases wherein it's not specified for this term or for this course, we will adapt 2015. Again ha, kapag hindi na i-provide or hindi na mention sa problem what provisions to use, automatically gagamit ka ng 2015. Unless specified, you need to follow what's in the problem or what you're being asked to do. Just take in particular or take a look on this one, dead load, live load, and earthquake. There is F sub 1 here. At the bottom, we have the caption that F sub 1 is equal to 1.0 for floors of public assembly for garage. Live load and for L greater than 4.5 kilopascal. It becomes 0.5 for other type of live loads. If you check NSCP, there are other manifestations of your live loads. But in here, kapag ka daw floor load ng public assembly, kapag garage live load that has L greater than 4.8, which is the value of your live load, you need to use F sub 1 equal to 1.0 as a factor. It becomes 0.5 otherwise. That's how you will interpret this load combinations. So I hope that this is clear. You can just write this simply on your index card for easy access, and familiar yourselves or be familiar with this two. Okay, at least this two. Kasi we will be utilizing those tools for our discussions. Continuing, design strength. No? By definition, the design requirement is your nominal strength multiplied by the strength reduction factor. If you would remember, I mentioned a while ago that if m sub n, or on my last video, m sub n, when multiplied by the reduction factor, it becomes your design strength or design requirement, which is also equal to your ultimate. That would be the ultimate capacity of your section. There are many ways to compute for your design requirement kasi it could be expressed in not just moment. It could be expressed taken from 409.5.1.2 for flexure. That's moment. Vmn should be greater than or at least equal to your m sub u. For the capacity should be greater than your demand. Okay? The left one is your capacity, and then your right one is your demand. Ano yung demand? Taken from the situation or the setting of your sections. Pwede rin siyang shear, which is V sub n should be greater than or at least equal to V sub u. Ito rin yung torsion, and then yung actual natin. Again, remember that this is taken from Section 409.5.1.2 of the latest code 2015. Okay? Sample, if your m sub n is your nominal strength, which is your internal resistance of a member, sometimes it would be termed as the internal resistance of a member. Again, for resistance, that's nominal. Now, computing for your ultimate, pwedeng ito yung mga term. M sub u could be meaning maximum, ultimate, or required moment. So be familiar with all of those terms and make sure that you will be able to understand or realize what is to be computed when using this combination. Sabi na nominal strength or internal resistance of a member, it's M sub n. If it's maximum or ultimate required moment, it is M sub u. By definition, we have your nominal moment as the capacity of a cross-section computed using the nominal dimensions and specified material strengths. On the other hand, your ultimate moment is the bending moment caused by the factored loads. Again, factored loads are 2000 war or 2015. Unless otherwise specified, you assume it's 2015, okay? Or you use 2015. This is a load effect computed by structural analysis from the governing combinations of factored loads. Your phi is the strength reduction factor used to account for possible variations in dimensions and material strengths and possible inaccuracies in the strength equations. So for being for the practice of conservative or being conservative and being safe, because you're a structural engineer. So life matters. You need to make sure that there are safety gates or safety havens in your designing, and one of which is your reduction factor. Ibig sabihin, yung most or maximum capacity, nominal capacity niya from the actual computed would be multiplied by your reduction factor, so it could have lesser values for the design or usage. Kasi yung i-induce mo naman or i-introduce mo naman na Vm sub n will be the one to serve as your limits na ito na yung safest because this has been taken for the reduction factor. This is to account, as mentioned, for uncertainties and inaccuracies because no one is perfect, and since no one is perfect, but still what we're doing is for the sake or the welfare of others, because we are civil engineers, we do structures, so we need to make sure that we are applying safety nets or being conservative in our design. Now, we need to understand what these reduction factors are. Okay? The reduction factors are taken from if NSCP 2001 here. Under flexure without axial moment in beams, the reduction factor is assumed to be 0.9. Ibig sabihin, for me to get my design strength, I can have it equal to my phi multiplied by m sub n. If I have my nominal resistance that can be computed, I can just adapt phi equal to 0.9 when my member is subject to flexure and it is without axial, or it means that it is moment in beams. So because this is USD in beams, kapag 2001, laging 0.9 yung gagamitin nating reduction factor. But when we move on to other topics wherein we are now discussing axial compression with or without flexure, we have what we call your tied columns and your spiral columns. Under tied columns, ibig sabihin, it would use 0.7 as a reduction factor. Under spiral columns, it would use 0.75. Again, these are your reduction factors phi. Okay, itong phi na to. Hindi pa natin gagamitin tong 0.7.75 kasi nagko-focus lang naman tayo sa beams as of now. In cases that it is against shear and torsion, the reduction factor is 0.85. And then for bearing on concrete, the reduction factor would be 0.7. So for 2001, we call it as reduction factors. But when we transition to 2015, it becomes strength reduction factors. So under table 421.2.1, ito yung una natin, no? We focus first on letter A. If it's moment, axial force, or combined moment and axial force, your reduction factor needs to range from 0.65 to 0.9. Later, we would understand why or how can we particularly or exactly compute for your reduction factor. Kasi hindi naman pwedeng range. Hindi naman pwedeng manghula within the range. Kaya kailangan exacto siya. But just an advanced knowledge, if it's what we call, we can determine your reduction factor from 0.65 to 0.9 when we establish that conditions of failure. In USD, there are three conditions of failure: your compression controlled, your tension controlled, and your transition. For tension controlled, automatically it will be 0.9. For compression controlled, it's either 0.65 or 0.75. Again, on the next discussion, it will be particular or it would be discussed how to determine those. If it's transition, it should be less than 0.9 but greater than 0.65. So it doesn't make sense as of now what your conditions of failures are, but in here, we denote that for members or action or structural element, under moment, axial force, or combined moment and axial forces, the reduction factor should be 0.65 to 0.9. For shear, it's taken to be 0.75. For torsion, 0.75. For bearing, 0.65. For post-tension anchorage zones, it's 0.85. For brackets and corbels, it's 0.75. For struts, ties, nodal zones, and bearing areas designed in accordance with strut and tie method in section 423 of the 2015 NSCP, it's still 0.75. Tapos for letter H, it is 0.9. For plain concrete, it should be 0.6. And for anchors in concrete elements, it should be 0.45 to 0.75. So in accordance with section 417, this is how you would use the code. For example, it tells you 0.65 to 0.9. Tapos sabi niya, or hindi ka marunong, ano kaya yung magiging specific? Dahil sabi nito, in accordance with section 421.2.2, kailangan pumunta ka doon. That's what we will be doing. Let's now transition or go to section 421.2.2. Under that, we are given a table for the reduction factor or strength reduction factor for members or elements subject to moment, axial force, or combined moment and axial force. Dito, nakita natin meron tayong tinatawag na conditions of failure. As mentioned a while ago, it's either compression controlled, transition, or tension controlled. Under compression controlled, it would be 0.65 or the other would be something else. Let me just fix this one because I think medyo naputol yung table. I'll pause the video first. Let me see. Okay. So what we have here are, as mentioned, compression controlled, transition controlled, or tension controlled. Dalawa yung value for compression, either 0.75 or 0.65. If it confirms that it is spiral, it should be 0.75. Kapag hindi naman or otherwise, 0.65 agad. Under transition, ito yung dalawang values using the formula. For spirals conforming to 425.7.7, it should be 0.75 plus 0.15 multiplied by this expression. Okay? ET minus ETY over 0.005 minus ETY. Tapos kapag other, gawin lang natin siyang 0.65 plus 0.25 of the same expression. Tension controlled, kahit anong case niya, 0.9 lang siya. Ngayon, paano natin malalaman kung transition controlled, compression controlled, or tension controlled? Ito yung tinatawag nating net tensile strain. Okay? We need to relate your tensile strain on other values. If your net tensile strain, which is E sub T, is greater than or equal to 0.005, therefore it is a tension controlled or under tension controlled failure. If your ET is greater than your yield strain or ETY but less than 0.005, therefore it's transition. Kapag ka naman nangyaring ET is greater than or is less than or equal to ETY, which is your yield strain, compression controlled siya. So later, we would see how can we apply this relationship. So it's like a rubric. After identifying the relationship of your strain on these values, ETY and 0.005, what we do next is we classify the type of failure. After classifying the type of failure, we check if it's under letter A or letter B. Kasi kapag letter A, those are spiral, no? Kapag ka spiral yung mga sections mo, ito yung mga reduction factor. But mostly, we could just adapt others. Kasi yung others yung ginagamit natin. Pero pag nag-columns tayo, dalawa na yon. Meron kasi tayong tinatawag na tied columns at spiral columns. Okay? So, in cases wherein sections classified as transition, it shall be permitted to use phi corresponding to compression-controlled sections. For deformed reinforcement, your ET sub y, or the yield strain, again, it's equal to Fy over Es, as discussed on the notations and symbols lecture. For grade 280, the deformed reinforcement, it shall be permitted to take exactly equal to 0.0024 your yield strain. So that is in conformation with section 421.2.2.1-2 or 0.2 of the NSCP 2015. Okay, so this would be further illustrated to you or discussed with you via next table or via new table, because mas clarified yon or mas simplified yon, and then look forward to having our sample problem or discussion. Next is, after table 421.2.2.2 or 0.2.2, do tayo sa 0.2.3. Ito naman yung for pre-tensioned members, no? Para din siyang ganun yung application. So after identifying the condition of near-end member, we identify the stress in concrete under service load, and then we compute the distance from end of member to section under consideration, and then we determine for your reduction factor phi. This is the stress calculated. If it's denoting as 1, ito, yung bracket sa 1, it means that the stress calculated using cross-sectional properties in extreme concrete fiber of pre-compressed tensile zone under service loads after allowance for all pre-stress losses at section under consideration. For number 2, it shall be permitted to use a strength reduction factor of 0.75. So I will no longer discuss this into details because I have no application of this section. We'll just focus on 421.2.2 and 421.2.1 as discussed a while ago. But for your convenience and for your future references or reference, This is your LTR equal to FSE over 21 multiplied by the diameter of your bars. If you will forget the notations, FSE is the effective stress in the pre-stress reinforcement after allowance. Ito yung kinumpute natin dati, yung FPS on our previous discussion under pre-stressed concrete. Yung DB ko, refer to section daw 425.4.8.1. Under the 7th edition of NACP is 2015. Okay? So much for your reduction factors. Next one is assumptions for concrete. What are the assumptions for concrete? It is assumed that your concrete cracks at a maximum strain of concrete equal to 0.003. Yung mga strain values na yan, it would be effective and it would be used when we are discussing strain diagrams for different situation or different analysis. Magiging helpful sa inyo kung laging tatandaan na E sub C is 0.003. In USD, what matters is for me, knowing the transform section, knowing your stress block diagram, and knowing your strain diagram. Pag ganon, kahit hindi na tayo mag-memorize ng formula, we can derive it on our own. I'll show you how those values or equations are derived. Accordingly, according to the NSCP, the depth of uniform stress block alpha is equal to your beta 1 multiplied by your C. Again, your C is your extreme compression fiber distance to neutral axis. NSCP 2015 section 422.2.2.4.1 tells us that the concrete stress of 0.85 FC prime shall be assumed uniformly distributed over an equivalent compression zone bounded by edges of the cross section and aligned parallel to the neutral axis located at alpha distance from the fiber of maximum compressive strain as calculated by alpha is equal to beta 1 multiplied by C. Later on, you would realize that on the notations and symbols video, sinabi ko na kapag ka siya ay WSD, yung neutral axis located exactly on the tip of your crack section. Dito naman sa USD, nagiging meron siyang distance between the two. In-over ko lang siya ha. Parang, anong ba ang tawag doon? Exaggerated lang yung distance na this is my neutral axis. Kung sinabi niya that your concrete stress should be 0.85 FC prime tapos uniform having a depth of alpha, ito yung interpretation, 0.85 FC prime. If you would remember your stress block to ha, on WST, USD to, on WST would look like this. It is triangular. Kaya meron tayong volume for this one. Parang ganyan siya, di ba? Pero dito, magiging volume na siya ng cube. Okay? So, anong magiging main difference? Ang main difference, yung aking compression nandito sa KD over 3. Kung mareremember nyo, KD over 3. Dito, dahil square siya or rectangular, ang aking compression is at alpha over 2. So, from this scenario or from this illustration, magkaka-idea tayo na, we can derive equations for flexure equation or for moment, no? Using this provisions. Kaya, binibigay muna natin yung provisions from the NSCP so we can effectively and more easily understand our discussion later. So we don't forget that your alpha is the depth of the compression block or your C is the depth of your neutral axis. When you're reading on other references, pwedeng ang gamitin na sa alpha is letter A. Huwag kayong malito, pareho lang yun. Continuing, under section 422.2.2.4.2 of the NSCP, your C is defined, which is the distance from the fiber of maximum compressive strain to the neutral axis. C is measured always perpendicular to the neutral axis. NSCP, beta 1, review lang natin yan kasi kasama yan sa mga assumptions na meron tayong value for beta 1. Also, for your convenience, your beta 1 are here. If your FC prime is greater than or equal to 17 but less than 28, I'll repeat, beta 1 is 0.85. If it's greater than 55, it's 0.65. If it's within the range of 28 and 55, you need to use this equation. In 2001, this is 30. No? Yun lang yung difference. Again, in 2001, it is 30. So you need to remember that. Or maybe take note of that. Yun lang yung nagbago. For 2015, this is one that we use. 0.85 times 0.05 FC prime minus 28 over 7. I hope that is easy for you to catch on or understand. I'll move on. Now, assumptions for non-pre-stressed steel reinforcement. This one is the convention, yung ating mga bars. The strain in concrete and steel shall be assumed linearly proportional to the distance from neutral axis, maximum at extreme concrete compression fiber, which is equal to 0.003, and bar centroid, E sub t, and 0 at neutral axis. So what does it mean? Later, you would see that the shape of your strain diagram is like this. Okay, like that. If this is my concrete section, ito yung steel bar ko, tapos ito yung aking neutral axis. Pwedeng ganyan. So, ito yung aking concrete, tapos ito yung aking steel. So, mamaya, mas ma-illustrate siya kung papaano siya naging ganon in accordance to these assumptions. Again, taken from NSCP. The design properties, on the other hand, are for non-pre-stressed bars and wires, the stress below Fy shall be Es times your steel strain. That means that Es is equal to Fs over your steel modulus of elasticity for strain. If you multiply this one, that's what you are dealing with this, or that's what we are describing here for stresses below. Dapat yung Fs ko ay less than Fy. Therefore, Fs could just be simply Es multiplied by strain in your steel. However, for strain greater than the corresponding Fy, stress shall be considered independent of strain and equal to F sub y. Bakit importante yung Fs? Saka yung importante yung Fy. In our analysis and design, we relate the yielding and non-yielding conditions of your steel for this one. If we are using Fs, we investigated, we analyzed, and it showed that it's non-yielding. Therefore, we can use the value of Fs, or we can utilize the value of your Fs. So, tanggapin lang muna natin na if it's Fs, it's non-yielding. If it's Fy, it is yielding. Anong ibig sabihin ng yielding and ng non-yielding? Kapag yielding kasi siya, ibig sabihin your steel yields, which would be under reinforced. No? Pagka naman non-yielding is F sub S siya. Kasi di ba meron tayong two ways to compute for your moment? Wala pa kasi eh. So, i-advance lang natin. Either ultimate compression multiplied by, assumably, we already discussed that the lever arm becomes the alpha over 2 now. And then this one is your tension multiplied by d minus alpha over 2. Under WSD, yung tension ko, ASFS lang siya. Pero kapag USD siya, yung tension mo pwede siyang AS, FS, at pwede siyang AS, FY. What's the difference? The difference is that because in USD, there is assumptions and then there's checking. Upon checking, you already determined that it's non-yielding. You can compute for tension as ASFS. If it's yielding, you can compute for tension as ASFY. On the other hand, under USD, the value of MU calculated from compression should be equal to the value of mu calculated from tension. Kaya we need to be particular on what values to use. Unlike your WSD, pwedeng yung ultimate moment mo hindi equal dun sa ultimate moment na ginamitan mo ng compression at tension formula. So it would make sense or a lot sense once we discuss the derivation and sample problems for this course. Alright? We'll just accept that this is taken from 422.2.2.1 of the NSCP 2015. Also, 2000 ES is your 200,000. Again, kuha lang yun sa code. Tapos ito yung sinasabi natin na cases for your steel stresses. So for case 1, the steel tensile stress is equal to Fs equal to Es Et as mentioned here. When Et is less than or equal to Ety. Again, if we remember, this one is your compression controlled. No? Yung aking relationship na yan. Remember that Ety is Fy over Es. For case number 2, Fs is equal to Fy when your Et becomes greater than your Ety. This is for case 1 and case 2 for yielding and non-yielding. So, mamaya, madidiscuss natin on what does it mean really in terms of analysis and design. For general singly reinforced beam, let us have this as the discussion. So, on WSD, yung aking flexure equation, it's only applicable to rectangular beams. O kaya kapag ang cut ng aking neutral axis for a T-section would be in between your flange and your web. Dito, any shape of your concrete, whether it's triangular, T-shape, or rectangle, ito yung basic or general singly reinforced beam. SRB lang siya ha, applied to for any shapes. Gagawin natin, we have a concrete that is cracking. The area of concrete is there, and then the effective depth is denoted. AS is the area of your steel reinforcement at the bottom. If we draw our neutral axis, we can therefore draw our stress block. According to the codes, provision, and assumptions we've discussed a while ago, this is your stress block. Uniform, parallel, equal to 0.85 FC prime. The depth would be alpha. Okay? Lagay ko lang to. Nahuli ata yung animation ng alpha. So, here, what we could look at is, balikan ko na lang, no? So, since this is already rectangular, your compression would appear at the center of your figure. The center of the figure is in connection with the centroid of your local concrete. Ito, yung sa aking shape na yan. Pareho lang siya. And then, the distance from the top to here would be equal to Z. Okay? Let's call it a Z because we are pertaining it as a general singly reinforced beam. Then, your T sub S or the tension in your steel is here. Denoted that it's going away to your tension bars. Tapos, the distance between the two, they are coupled, opposite in direction but equal in magnitude. If this one to this one is D minus Z, that's the lever arm between the two. And from the code, or as we remember pala muna, C can be measured from the extreme compression fiber, maximum compression fiber, to the neutral axis. But this time, we are inducing a new value which is your alpha. Your alpha is the depth of your compression block. If we remember, this is a volume, no? Yan, magiging volume siya. So with that volume, we can compute for C, which would be 0.85 FC prime multiplied by the height alpha multiplied by the base, which is B. Kasi ito base to. Saan natin nakuha yan? Dito. Base lang din siya. But we will stop with this first. Ito muna. Yan muna yung ating kunin kasi yun yung magiging basis natin for the strain diagram. Paano yung strain diagram? Sabi niya, yung strain sa concrete saka sa steel dapat proportional. Tapos daw, yung aking strain at neutral axis should be 0. That's why it's here meeting at 0. Concrete crashes at 0.003, I will reflect it. And then, your strain on steel depends whether you're using Fs or Fy. So we will denote this as E sub T. Denoting that this one is the value of your extreme compression fiber to neutral axis, the remaining one here at the bottom would be D minus C. So this would be the basis of our basic equations for SRB. Again, we're particular depending on the area of your concrete. Now, the area of your concrete now is not limited to rectangular. Kasi yung dati nating derived equation or flexure equation, it's only limited and to be applied to concrete or area of concrete that is rectangular above the neutral axis. Ito, kahit ano na siya. So what do we mean by that? Pupunta na tayo sa basic equations. So una, yung concrete compression. Di ba napakita ko na kanina that it is equal to 0.85 FC prime multiplied by the area of your concrete. Ano yung area ng concrete? Pwedeng equal to alpha multiplied by base kapag rectangular. Kapag different yung shape, i-denote mo na lang kung ano yung shape of your concrete. 0.85 FC prime is constant. Again, that's only taken from the figure a while ago. Also, for steel strain or for steel tensile strain, the area your concrete is assumed to crash at 0.003. Therefore, ET can be computed with this value, 0.003 times D minus C over C. How did we come up with that one? If this is my strain, which is proportional, I'll term this as ET. This is my EC, which is equal to a value of 0.003. And then remembering that the depth to neutral axis from compression fiber is C, the remaining would be D minus C. Applying the strain compatibility or ratio and proportion, we can arrive with or derive this formula. Gawa natin C over 0.003 is equal to D minus C multiplied by E sub T. If we solve for the value of E sub T, this would result to, or this would be simplified on this form. Okay? Ilagay lang natin, cross-multiplying 0.003 D minus C over your C. Something like this. Okay? So, either you remember the concept, or if you are a kind of student who remember formulas, okay lang din yon. Or who remembers formula, pwede naman yon. Pero what I suggest is, it would help if you have written this on an index card, because on an index card, what happens is it's easy access for you, and from time to time, you don't need to go back to the whole lecture. So, magiging beneficial sa'yo. Continuing, for the tensile stress at concrete is equal to 0.003. Paano natin nalaman to? Di ba alam na natin na E sub T or E sub S is equal to your Fs over Es. Ano ba yung Es? 200,000. Diba? Megapascal. Ano ba yung Et? That's 0.003 D minus C over your C. If you cross-multiply, we can compute for Fs. Now, again, you don't need to memorize but understand the concept of your stress block and your strain diagram for easier understanding and for easier derivation of formulas. For non-yielding tension, sabi natin kanina, ano ba yung yielding or non-yielding? It becomes non-yielding if we have determined that your Fs or the calculated stress in steel is less than your Fy. Ano yung Fy? Binibigay ito. This is the yield strength of your steel. Pag ang nangyaring relationship upon analysis and design is that Fs is less than Fy, it should be assumed already that your tension steel is non-yielding. Therefore, the formula to compute for the tension is As Fs. On the other hand, what we have is your yielding in tension steel. Ibig sabihin, the calculated Fs turns out to be greater than or at least equal to Fy. Therefore, for you to compute for your tension, your general equation or basic equation would be As Fy. Why is this important? I have the force in terms of compression. I have the reinforced in terms of tension, either yielding or non-yielding, it needs to be specified. Therefore, under basic equations, you can compute for your nominal moment strength. M sub n is equal to compression multiplied by D minus Z. Ano yung Z? That's the location of your compression at the bottom. Ano yung D minus C? That's the distance, di ba, between your couple. Your C and then your T. So, ito yung aking kanina na D minus C. So, we are now creating new equations for our USD. This is the basic equations only applicable to singly reinforced beam. Okay? Pagka naman design moment strength, phi mn, phi, this is the reduction factor for 2001 or strength reduction factor for 2015, compression and tension. If you could take a look lang, your tension again, as you remember it could either be ASFS or ASFY. How would you know? You would know when you will determine if it's yielding or non-yielding. Alright, as easy or simple as that. However, there are cases wherein because of vast use of rectangular sections, therefore, it would be easy and it would be helpful for us to generate equations for SRRB or singly reinforced rectangular beam. But before we do that, we need first to understand what are your reduction factors. So under this lecture, di ba sabi ko meron tayong simplified presentation of our reduction factor. Ito yung failure, compression controlled, tension controlled, transition controlled. Paano malalaman? Kunin tong mga conditions na to. Pag pumasok dun sa mga ganyan, ibig sabihin, let's say, upon computing ET, ano yung ET natin? From our previous slide, it is 0.003 multiplied by D minus C over your C. If it turns out to be greater than or at least equal to 0.005, it is therefore tension controlled. As easy as that. Kapag compression controlled naman, kapag beams at tied columns yung dinedesign mo, automatic 0.65. Kapag spiral columns, 0.75. Pag transition, automatically use this one unless it is spiral. So, ganun siya kasimpleng tandaan ngayon. It's just a recall of what we've discussed a while ago. Ito ngayon ang nangyari is that more simple. So under section 421.2.2.1, we don't forget that ETY or your yield strain is computed to be Fy over ES. Ano yung Fy? That's your yield strength of your tension bars. For grade 280, binalikan lang natin to, your ETY is permitted to be equal to 0.002. So those are, your reduction factors for 2015, for 2015. These are your reduction factors in terms of failure for tension controlled, compression controlled, and transition controlled. So, na-mention ko kanina, mostly naman nagiging rectangular siya. So, gawin na natin is, mag-derive tayo ng equation for singly reinforced rectangular beam. This means that what we are going to come up with is only applicable to singly reinforced rectangular beam. A typical section looks like this with area of steel, base, and effective depth there. If it crashes, the neutral axis is slightly below the area of your concrete above. No? What happens is when we draw the stress block, ito siya. It would be your 0.85 FC prime wherein your compression happens to be 0.85 FC prime alpha times B. Paano nalaman yon? This is base, di ba? From the geometry. This would be volume. Yung volume na yan has a base of B or a width of B. Tapos ito, alpha. Pag minultiply natin lahat, getting the volume, area times the height is 0.85 FC prime alpha B. We're not changing anything. We're just applying what we have learned so far. That's taken from the centroid of your concrete. Yun yung alpha ko. Di ba nga rectangular siya? So, ilagay ko na kaagad na alpha over 2 instead of Z. Kasi yung Z ko for SRB. That's a singly reinforced beam. Ito particularly for rectangle. Tension could be computed as ASFY if it's yielding or if it's ASFS kapag ka non-yielding. The distance between the two would be D minus alpha over 2. Inaano lang natin ginagawa lang natin siyang applicable for rectangular beams kaya meron tayong slight changes. On the other hand, the strain diagram is still proportional for concrete and for steel, and then EC is 0.003 and ET is Fs over Es. Okay? Assuming that it is, that's the safe value. Pwede naman siya maging Fy over Es. Pero pag nangyari yon, we would see on the next discussions. This one is your C. I think wala naman tayong question dyan kasi ganun pa rin naman From the compression, maximum compression fiber to neutral axis, and then D minus C, yung aking lever arm. If we took out or take out this one, this section, if we will take out this section and proceed with the derivation of formula, what we could have is this. If we remember, your alpha from the code is actually equal to beta 1 multiplied by C. So, gagamitin natin siya in deriving your equation. Because this is in equilibrium and compression is equal to tension, we can say that in WSD, moment is taken as compression times JD or tension times JD. Let's consider compression. Ito. Pero hindi na natin gagamitin to kasi ito ay for WSD. Gamitin na natin yung USD na the lever arm is D minus alpha over 2. C is your compression, and therefore, we can say that moment is 0.85 Fc prime alpha B multiplied by D minus alpha over 2. Remember that your moment could actually be expressed in terms of compression by allowing the value of alpha become beta 1 multiplied by C. Beta 1 is having values ranging from 0.65 to 0.85. Your C is the depth of your compression block. The depth of your neutral axis, D minus alpha. So you can remember this already or you can save this equation now. If not, you can just remember C is equal to T. Tapos remember how your provisions are given and assumptions given to your reinforced concrete under USD. Using statics also, considering the tension, no? Ito yung ating dati, tension multiplied by JD. Diba? Ngayon, ayaw na natin yan. Ang gusto na natin is yung aking USD. It becomes tension multiplied by D minus alpha over 2. There are two possible ways to compute for moment, but you need to determine first whether it's yielding. Pag yielding, ASFY, D minus alpha over 2. Kapag non-yielding, ASFS, D minus alpha over 2. Those are the derived equation, these are the flexure equation or the general equation for SRRB. It's similar to your 1/2 fact Justin Bieber D squared, okay, yung ASFS, JD. Pero dito, particular tayo, specific tayo na pag yielding or non-yielding, i-determine mo muna for you to effectively compute for your moment. Bakit? Kasi you need to have exact similar values taken from this equation and this equation. Tapos upon understanding if it's yielding or non-yielding, dapat tama din yung magamit mong equation para maging equal dun sa computed value. Dapat isa lang yung sagot na moment. So taking that into account, the general equation or basic equations for SRRB is that taking compression equal to tension, we have 0.85 Fc prime alpha B equal to ASFY. In here, we assume it's yielding. That's why ASFY. We can compute for alpha to be ASFY over 0.85 Fc prime of B. On other presentations or other ways to compute for alpha, we can express this in terms of rho. If we multiply it by a factor of 1, D minus T, we're not changing anything from the equation because D over D is just 1. We have AS over BD would be equal to rho, if you can remember. So, pwede nating masimplify yan by saying alpha is also equal to rho FYD over 0.85 FC prime. Remembering rho is AS over BD. Kung gusto naman natin gumamit ng omega, yung omega ko is actually equal to rho Fy over Fc prime. This is what we have. Omega here is different from the omega of pre-stressed concrete, no? Kasi yung sa pre-stressed concrete ay similar lang siya, pero kasi merong omega at omega prime. Dito naman is isa lang siya, omega Fy over, rho Fy over Fc prime. Tapos, the design moment capacity becomes Vmn multiplied by Vc times d minus alpha over 2. Pag tension, ito siya. Always remember that for tension, dapat isa lang sa dalawa. Kaya kailangan mo determine mo kung yielding or non-yielding. Para yung sagot nito ay similar sa sagot nito. Dapat ganun lagi. Isa lang yung final answer. For the derived equations, Vmn is equal to V times rho Fy BD squared multiplied by 1 minus 0.59 rho Fy over Fc prime. Vmn equal to V omega Fc prime BD squared times 1 minus 0.59 omega. So how did we come up with the derived equations? So kunin natin ulit yung ating illustration. To the basic equation from compression, Vm is equal to 0.85 times V Fc prime alpha B multiplied by d minus alpha over 2. We already computed for alpha from our C equals to T, di ba? Bigay ko lang kung bakit naging ganyan yung alpha para malaman mo na hindi mo kailangan mag-memorize. Ano yung compression natin? 0.85 Fc prime alpha multiplied by B equal to, assuming it's yielding, AS Fy. Rearranging the equation, solving for alpha, it becomes AS Fy over 0.85 Fc prime times B. Tama ba yon? We need to express this in terms of rho. So I will multiply it by a factor 1, which is d over d. Your B times d times AS is actually equal to rho. Rho Fy, the remaining value here is the numerator d over 0.85 Fc prime. So gagawin natin daw, ilagay daw natin to dito. No? Alpha is equal to rho Fyd over 0.85 Fc prime sa equation ng aking Vm. What would happen when that is the case? I will erase and then this would turn out to be yung alpha ko, it becomes now rho Fyd over 0.85 Fc prime. So pag ni-rearrange mo siya and then sinolve mo yung value for Vmn, you would see that it could be expressed in this equation. V rho Fy multiplied by BD squared multiplied by the quantity 1 minus rho Fy over 1.7 Fc prime. Pag sinimplify mo pa further, yung 1 over 1.7, ito yung equal niya. 0.59 rho Fy over Fc prime. So there are also instances wherein further derived equation are here expressed in omega. So it could be phi Fc prime omega BD squared multiplied by 1 minus 0.59 omega. Or RBD squared times your phi. Tandaan natin na ano ba yung ating flexural resistance, which is R, and yung ating reinforcement index omega. This is how we can solve for this. Para makita nyo lang kung bakit naging ganun yung mga derived equations natin. So for analysis and design, the derived equation is only specific for tension control. Kasi nakakita natin, yielding yung condition Fy. So I will teach you how these are applied in the next videos maybe. Kasi medyo hindi ko na ata kayang malagay dito. So next video na lang siya on how we can apply your derived equation in solving analysis and design problems for ultimate strength design or USD. So it's good lang na at least we already know na aside from the basic equations for SRB and SRRB, we also have the derived equations for SRRB. Pero because this is for SRRB this is only applicable for singly reinforced rectangular beams. For the steel tensile stress for SRRB, there are two cases as we know. Yung una is non-yielding. For us to determine whether to use Fs or Fy, we need to know the relationship between your Fs and Fy. If it becomes Fs less than Fy, it's a non-yielding condition. Therefore, Fs can be computed to be Es multiplied by the strain in steel. Yung Es ko, 200 gigapascal, and Es or strain S ko ay epsilon S could be tensile strength strain when concrete crashes. Anong ibig sabihin nun? This could be your strain diagram. So, as we know, dito usually EP to, di ba? Pareho lang naman yon, wala namang masyadong pagkakaiba. So, it could go both ways. So, gawin natin E sub S, tapos by strain compatibility or ratio and proportion, we could have this relationship. EC over C is equal to ES over D minus C. Ano yung D minus C? Ito po, D minus C. When we compute for ES, nakuha na natin kanina yan, EP or ES is just equal to 0.003 multiplied by D minus C over C. Pareho lang yon, walang problema doon. Basta ang alam natin, ET or ES is your tensile strength strain when concrete crashes. Okay? Continuing with the equation, we already have derived before, just a recall, Fs would be 600 times D minus C over C. Bakit? Kasi ito nga, Fs is Es multiplied by the strain in steel when concrete crashes. That's for case 1. That's non-yielding. For case 2, which is a yielding condition, Fs is taken or understood to be greater than F sub y. This is when we use Fy instead of Fs. Anong ibig sabihin nun? When computing for tension, ASFy would be your formula. Okay? In addition to the provision and assumptions, what we have is your conditions of failure. Balikan ko lang to sa inyo para hindi na tayo masyadong malito pa. Yung compression-controlled failure, yung transition-controlled failure, at saka yung tension-controlled failure. Pag compression-controlled, ito yung ibig sabihin is an abrupt collapse. The concrete crashes before steel yields. This means that your ES or the strain in your steel when concrete crashes at 0.003 is less than or equal to your yield strain. Ano yung yield strain? Fy over Es. This means that when it is grade 280, we are permitted to use 0.002 automatically for ETY. What would be the reduction factor? Dalawa. Kapag beams or tied columns, 0.65. Kapag spiral columns, 0.75. Pag tension controlled naman, this is when your steel is way beyond yielding before concrete crashes. Also, it is called your gradual collapse due to yielding phase. This is where your ES or the strain on your steel reinforcement when concrete crashes is greater than or equal to 0.005. So whether it's spiral column, tied column, or beam, reduction factor is 0.9. Lastly, for transition failure, this is when your steel just yielded. Dapat yung ES ko follows this relationship. It is greater than ETY but less than 0.005. These are the three cases wherein your ES is compared to ETY or 0.005. Your reduction factor should range from 0.65 to 0.9. How can we know what to apply? You use this equation. If it's a beam or a tied column, it's 0.65 plus 0.25 ETY minus ET minus ETY over 0.005 minus ETY. Kapag ka naman spiral column, yung isa, 0.75 plus 0.15 multiplied by ET minus ETY over 0.005 minus ETY. Consequently, under conditions of failure, for the reinforcement of strain, for ET or ES, it should be greater than or equal to 0.004 to maintain a tension-controlled design. Ibig sabihin, pag nagde-design tayo, we could provide the maximum value of your steel strain to be equal to 0.004. But this is just in an advanced learning because we are not designing yet. We are analyzing on this stage first. For section 409.6, the reinforcement limit, it tells us that the area minimum for your steel should be greater of the following: 0.25 FC prime square root over Fy BD or 1.4 Fy BD. So upon computation and upon solving the values, kung ano yung mas malaki dyan, yun yung adaptive or provided AS minimum. Why is that important? Under the USD, design or analysis, you always compare your computed or actual AS to your AS minimum. Dapat lagi siyang greater than or equal to. There are provisions wherein when your AS becomes less than, you need to provide AS minimum instead. Hindi na mas pwedeng bumaba pa kasi nga minimum siya. That is the provisions from the code. As an important note, before we transition to problem solving, we have your balance condition where there is simultaneous yielding of concrete and steel. This is the transform section and then your stress block. Okay? Taking into account that because it's already balanced, I denoted that the area of your steel is under balance condition. The strain diagram would be like this one. It is, balance condition is always yielding. That's why we use Fy. Concrete steel crushes at 0.003. And then your effective or your depth of your compression block, the depth of your neutral axis is now C balance. Ibig sabihin nito, magbabago din to. Alpha balance, alpha balance, alpha balance. Okay? Please take note of that. Ito, just a typographical error. Dapat D minus, C balance. Bakit natin ginagawa yon? Para particular tayo on different conditions. Kapag C sub 5, C sub 4, o kaya C balance, yun yung mga nagiging differentiation natin. So, absorbing this illustration, we can now yield the equation for your balanced steel ratio. No? Here, under compression is equal to tension, we have 0.85 FC prime alpha balance times B equated to area S balance Fy. Again, that's the balance steel ratio. We could say that because alpha from the NSCP is C multiplied by beta 1, therefore alpha balance is equal to C balance multiplied by beta 1. Dito, bakit naging yung C balance ko equal to 600D over 600 plus Fy? Punta tayo dun sa strain diagram. Eh di ba sabi nga sa strain diagram, ET is Fy over ES. Tapos, concrete crushes at 0.003. This would be your C balance. Therefore, this is D minus C balance. What would be your strain compatibility? The strain compatibility is the ratio in proportion of these triangles. I'll show you. Etong isang to, ayan, yung maliit, tapos yung malaki. Ay, sorry. This one. This big triangle and this one. So, pag kinuha mo yung ratio and proportion yan, ito yung lalabas. EC over C balance is equal to Fy over ES plus 0.003. Computing for C balance, taking into account that your ES is 200,000 megapascal. No? Lagi natin wag kakalimutan yun. So, the only unknown now becomes C balance. So, inilagay lang natin to dito. Kasi we're computing for your raw balance next. Gusto nating ipakita kung ano yung possible value for your raw balance. Why? Because as mentioned a while ago, your derived equation can be applied by determining whether it's compression controlled or tension controlled. Pag tension controlled, pwede. Pag compression controlled, kailangan basic yung gawing solution. C is equal to T. Itong raw balance na ito nakakatulong siya because when you compare that to the actual raw, yan, to the actual raw, masasabi mo siya na compression controlled or transition controlled. Pero I will not venture on that yet. Basta right now, just remember that the formula for raw balance is 0.85 beta 1 Fc prime over Fy multiplied by 600 over 600 plus Fy. So that's the provisions and assumptions of ultimate strength design for a singly reinforced beam and singly reinforced rectangular beam. The next discussion would be about analysis of SRRB strength capacity by sample problems. So I have prepared ample amount of sample problems that would manifest or would illustrate the application of our assumptions and provisions. That would be discussed on my next video. Thank you for watching and see you on part 3 of Ultimate Strength Design of Beams. God bless you.